We often add caching to make our systems faster. Just put a cache in front of the database and the performance improves. Simple, right? But in real systems, caching introduces new challenges. So why is something so simple, so hard to get right? Let's figure out. When the server needs data, it usually asks the database. But the databases are not that instant. First, the request may travel over the network. Then the database may need to read from disk, and disk operations are slower than the memory operations. Now imagine thousands of users requesting the same data, like a product page or user profile. So we are hitting the database again and again for identical information. So that's expensive as well as slow, and that's unnecessary. So basically, instead of that, for solving this, we need some strategy which can cope up with the network latency, can reduce the disk operations, and also the concurrent load problem. So here comes the concept of caching. Okay. So a cache is a fast and temporary storage layer. It usually lives in memory, which is much faster than the disk. The idea is simple. If we have already fetched some data once, then we keep it close to our server. That basically saves up our network calls directly to the database. Now let's see how actually a cache works in practice. So let's make this more concrete. So most caches store data as a form of key value pairs. For example, imagine we store a user's profile picture using a key like C1 pics and having corresponding the image URL. Now suppose a user named C1 or client 1 sends a request. Hey server, show me my profile picture. If the entry is found in the cache, then that's a condition of cache hit. So we immediately return the profile picture back, and in this case, no database calls are needed. But suppose this key in the cache is missing. Then the server goes to the database, fetches the profile picture, stores it in the cache using the same key, and then returns it to the user. So the next time this user asks, we don't need to hit the database again. We simply query our cache and get back to the client. So this is the basic idea behind caching. So at this point, caching sounds amazing. So why don't we not store everything in the cache? So well, because cache lives in memory, and we know memory is limited. It's also expensive, as well as it's not meant for long-term storage. Unlike a database, cache is not a source of truth. If the cache crashes, then what will happen is we'll lose all our data. On the other hand, databases are persistent and the caches are temporary. So basically, a cache is like a performance layer, not a data storage system. Now, if we try to store everything in cache, so we are basically turning it into a very expensive and fragile database. So cache solves one problem, speed. It is, but it introduces another problem. Can you guess what? Yeah, it's correctness. Here's where the things start getting complicated. Suppose the database gets updated. Maybe the user changes their profile picture. The database now has a new value, and our cache still holds the old one. Now, when there is a new incoming request, we are returning the outdated data, and this is called stale data. This is the core problem with caching. Another common pattern is cache aside. So here, our applications controls the cache. If there is a read request, it first checks the cache. If there is a miss, then the entry is read from the database, and subsequently, the data is written to the cache. Subsequently, on writes, if there is write request, then update is propagated to the database, and then the corresponding entry is either invalidated or deleted from the caches. This gives flexibility. But now the application logic becomes responsible for keeping things consistent. Now let's look at a more realistic scenario. So suppose we cache the popular product page with a TTL of 5 minutes. So at minute 5, the cache entry expires. Now imagine thousands of users request that product at the same time. So since the cache has expired, every single request becomes a cache miss, and every request hits the database. Instead of spreading the load, we just created a sudden spike. So this is called cache stampede. Now, moving to why the cache stampede is dangerous. So basically, the database is usually the most expensive component. If it gets overwhelmed, the entire system can slow down or even crash. So ironically, a feature meant to improve the performance can become the reason for failure. Moving to how systems handle it, there are multiple strategies. First is locking. In this, only one request rebuilds the cache while the others wait. In request coalescing, it basically merges the identical requests. And in staggered expiry, it guarantees that not everything expires in the cache at once. And in the background refresh approach, the cache is updated before it gets expired. So let's step back. Caching absolutely makes system faster, but it also introduces new problems. Stale data, invalidation trade-offs, and traffic spikes like stampedes. It's not just a performance trick, it's a design decision. At its core, caching is a trade-off. We gain performance, but we must carefully manage consistency and system load. It's easy to add a cache, it's much harder to design it correctly. And that's why caching is harder than it looks. Thank you, guys.